All right. Very good evening, everyone. My name is Varnit Kapoor, and today I'll be starting with week 2 of the tutorial of thermodynamics. So I hope everyone has watched the lecture videos of the week 2 uploaded on the portal, as well as the tutorial one recording, which was already uploaded on the YouTube. Okay, so let me share the screen and let's start our tutorial. Okay, I think my screen is visible now. Yes, great. Okay. So let us start with the next topic of in the continuation from the previous tutorial. So today's topics will start with energy interactions. So all the videos are uploaded on the YouTube. You can check week by week as we progress, as well as the notes PDF of the tutorial one are uploaded on the Google Sheet and the Google Drive. From there you can see. Okay, so what there's a term called work. So what do we understand by the term work? So in a layman term, I think I'm not visible. Okay, so I was saying about the work. This works fine. Yeah. So work is nothing but, in a layman term, we can say that is some force we have applied over the body, and that body has displaced by some distance. If I have a pencil, if I apply a force on it and it will displace, then a work is done on the pencil. Right? But in a scientific manner, what do we say work? So work is nothing but is said to be done by the system. So we have done water system surrounding everything in the tutorial one. So work is said to be done by the system if sole effect on the things in that system external to the system. Work is said to be done by the system if sole effects on the thing which are external to the system gets reduced to a raising of weight. Okay, if you are raising a weight and the things are external to the system, then a work has been done. But in actual, weight may not be raised. There can be some other scenarios as well. So let me first write, then you'll understand. Okay. So work, the first definition is, okay, I hope everything is visible, whatever I'm writing. Work is said to be done by the system if sole effect on things which are external to the system. External to the system. Very important line. Whatever things are external to the system gets reduced to raising of weights. And point to be noted that the weights may not be actually raised. Some another scenarios can also progress, like the weights Like, suppose I take an example of a battery fan system kind of thing. Battery fan motor is there. So suppose my first case is I have a battery which is connected to some scenario called motor. Okay, and this is connected to a fan. All right. The thing is, what is system here we are considering? Suppose, so I'll make 3 copies of it. Copy. I think it didn't work. Yeah, cool. And I'll create one more copy of it. Paste. Yes. Yeah. All right. I have 3 scenarios I'll take. So my first scenario is if my system is only battery. This is only my system. If this is the only system, then whatever external to the system, basically battery is connected through a motor and that fan is rotating. So if fan is rotating and which is external to my system, then our work has been done. Okay. Okay. In second scenario, if suppose motor as well as battery are my system, still again fan is rotating. So again, a work has been done on this. Work has been done by the system. Okay. So both of them are correct. This is also correct scenario. This is also correct scenario. Here you can see. But if a scenario occurs that my whole of it is considered to be a system, then there is nothing external to the system left. Then and work has not been done. No raising of bit or moving of fan is there. Okay, so that is a scenario. We will take a convention that if work is done by the system, we will generally say it is positive in nature. If work is done on the system, then we'll take it as a negative. So point here that is work done by the system is considered as positive and work done on the system is considered as negative energy. Now, what are types of work? There are 2 types of work. One is closed system work, another is open system work. Let me write. First, closed system. This is also called as non-flow work because nothing will flow out of the boundaries. Because you know what is a closed system? Something where only energy interaction takes place, no mass interactions from the last tutorial. Open system. And this is called as steady work. Okay. Steady work. One thing is that to obtain a closed system work, whenever you want to obtain a closed system work, the area under the PV plot, pressure volume plot, should be projected on volume axis always. Right here. To obtain closed system work, area under PV, pressure volume plot, should be projected on volume axis. What do I mean? If you have a pressure versus volume plot, and suppose our graph is look like this, okay, from state 1 to 2. So the projection of this should be always on the volume axis when you are defining it as a closed system work. All right. Okay. And how the expression will look like? Work done for closed system will look like P into change in volume, PdV. And when you are dealing with an open system work, area under the PV plot should be projected on pressure axis to obtain open system work, area under PV plot should be projected on pressure axis. So suppose, so this is pressure versus volume, same graph. From 1 to 2, you are going like this. But how your projection will be now? It will be on pressure axis. So, and the formula or the work is described as negative of V into change in pressure. Okay, change in pressure. We'll understand why negative sign comes in later part. So closed system work is PdV, open system work is negative of VdV. Simple. Now coming to the expression of closed system work for different processes. Suppose you have a process that is constant volume process, constant pressure process, constant temperature process, no heat exchanges there, adiabatic process, polytropic process. For all these processes, what are expressions for the work done? Okay, me write expression of closed system. Only I'm saying about closed system. Closed system work for different processes. Okay, so suppose first is volume is constant. So what does this process is called? Isochoric process or isometric process? Isochoric or isometric process. So whenever it is said process is isochoric, isometric, or volume is equal to constant, all are same thing. So when a process is like this, you know that plot looks like this. This is a PV plot and volume is constant. So process will be something like this. So from state 1 to 2, and we are dealing with closed system. So projection will be on the volume axis. The projection is here on the volume axis. Let me draw it once again. From state 1 to 2, the projection will be on the volume axis. Change in volume is not there. So work done is PdV. Since volume change is 0, P into 0 is 0. So for an isochoric process, work done is 0. Closed system work done is 0. Second scenario, when pressure is constant, or what do you say it as? Isobaric. Or you also say it as isopistic process, isopistic. So what is the pressure versus volume plot looks like? Because it's a pressure constant, so it will be like a horizontal line from state 1 to 2 and projected on again volume axis. Okay, because closed system work, that is this area, and work done is nothing but PdV. So P, for a constant pressure P, what is V final minus V initial? Okay, so that is your V final is V2 minus V1. So that is V2 minus, because process is growing from state 1 to 2. Next, temperature is constant. Temperature T is constant. Another way, you can say it as an isothermal process. Or you can say it as a hyperbolic process. So all are same thing. Okay. So from the law, ideal gas law, which we did in the last tutorial, EV is equal to MRT. Okay. So MRT is nothing but constant, because M is constant, R is constant, and temperature, you are saying that it's an isothermal process. So it's nothing but a constant C. So volume will be nothing but C over pressure, constant over pressure. And what does a graph look like for this process? Because I'm saying it's a hyperbolic. So this is a kind of graph, a hyperbola in nature. So projection will be again on y-axis, oh sorry, volume axis. But we have to calculate the work done expression. So that is nothing but P dV. So what you can write pressure as from here, either you can write, let's write like this. Pressure is nothing but constant by volume. All right. So put this pressure here, constant by volume dV integration from initial state to final state. So C of dV over V from initial state to final state. You know its integration is log. So that is C ln V final over V initial. Or you can also write, because pressure is constant by volume, or volume is constant by pressure. So both are inversely proportional here. So you can write here C ln V initial by V in terms of pressure. Okay, put the values. So that is your work expression for the work. Great. Because we know that constant is Pi Vi is equal to P final V final. Your constant is PV, P initial, V initial, P final, V final, or MRT initial or MRT final. All are same thing. Okay. And it is a hyperbolic process, and it is a rectangular hyperbola as well. Rectangular hyperbola. Why? We'll understand that. Don't worry. Also, during an isothermal expansion, because from 1 to 2, if you see, your volume is increasing from initial to final. Okay. So because your volume is increasing on the axis V1, V2. So during expansion, volume is increasing. So work net will be a positive value. Final volume is greater than initial volume. The work done will come out to be positive. That means work has been done by the system. So whenever you are expanding here in isothermal process, due to some expansion, volume is increasing and work is done extracted out of the system, taken by the system. But during a compression process, if you go from 2 to 1, then your volume is decreasing. Okay. So what happens? That means volume is decreasing. So this value is less than this. Numerator is smaller. So your work will come out to be a negative value. Log will come out to a negative. So that means work is done on the system during the compression process. So in an IC engine, if you see, we provide work done over the system. Whereas when you extract the work out of the system from the engine, in the there are four cycles. That's a four process cycle. So the compression stroke, work done by this on the system, and during the expansion stroke, work is done by the system, on the system, by the system. And anyways, so I'll write this point. During isothermal expansion, this implies volume increases. This implies work net which you get is positive. That means work done by the system. Second scenario, then during isothermal compression, volume increases. So work net is negative. Work done on the system. That's the sign convention which we took. Okay. Now question may arise, why PDV is the work done chosen for a closed system? So as we know that for a closed system, only energy interaction is taking place. So any effect of the surroundings on the system, like resistance you can say, or outer pressure effect isn't taken in a closed system. No energy interaction is happening from this. Sorry, no mass interaction is happening, only energy interactions are happening. But closed system has only energy interaction. So any effect from the surrounding resistance, if you have, that is like a external pressure effect isn't taken. So therefore, there is only expansion or contraction. Whereas in an open system, work done is negative of VDP because here surrounding effect resistance is taken into the account. So therefore mass and energy interaction happens. And in open system, there is a control volume scenario which we should take because system is open. So control volume, control boundaries are there, which will come into the later part. Okay. So closed system is basically only energy interaction taking place, no external surrounding resistance takes into account. So only either expansion happens on the system or contraction happens. Whereas in an open system, both mass and energy interaction takes place. So effect of the external resistance, that is pressure of the outer pressure and ambient pressure effect will come into account. Okay. I'll write this note as well. PDV is taken as closed system work since closed system has only energy interaction Therefore, someone has tried to join. So closed system has only energy interaction, and therefore you can say that effect of the surrounding, any effect of surrounding resistance that is outer pressure effect isn't taken. So there is only you can say expansion or contraction. That is why volume changes. PdV, volume change, expansion or contraction happens. Okay. Whereas in open system, work is VdP because surrounding effect resistance is taken into account. And since mass and energy both takes place in open system, okay, all right, okay. Now coming to the next process, that is adiabatic process. Fourth, so adiabatic process is that process in which there is no heat interaction takes place between system and surrounding. We'll come to the definition of heat. Okay, don't worry. So far we are dealing with work. So let me first finish with work. So process in which there is no heat interaction takes place between system and surround. All right, that is dq change in heat is 0. Example, you can have an insulated vessel and it follows a law, the adiabatic process. It follows PV raised to the power of gamma is equal to constant. Okay, where gamma is in the last lecture also we did Cp by Cv adiabatic index, where gamma is adiabatic index, that is Cp over C. All right. So Suppose I have a system like this and it is insulated. So there is no insulated heat interaction from the surrounding. So temperature, what can happen? Suppose if you have a scenario like fan is there, some kind of fan is there, or a fan is there, it is insulated. Okay. So fan is rotating. Temperature of inside room here, inside the, suppose this is a cabin or a room which is insulated. Temperature of the inside room can increase because of fan or cooler or heater, but there is no heat interaction with the surroundings. Always remember. I'll write this point. Important point. Temperature of inside because of the source which you have put. You have put a fan. Air circulates. There may be a friction, bombardment of air particles. Because of that, heat can increase. If you have a room heater, because of that element, heating element inside the room, it may increase, but not any kind of energy interaction outside with the outside surroundings. Okay. Inside room can be changed by fan, AC, cooler, okay, but no heat interaction with the surrounding. Right? Okay. So as I said, the relation which has been followed, PV raised to the power of gamma is constant. This only works for reversible adiabatic process. We understood what is reversible or reversible. No path shouldn't change, follow the same path. So this relation only works, only valids, only for reversible adiabatic process. And we can write in the way V initial raised to the power of gamma is equal to P final V final raised to the power of. Now the expression for the work out of it is, you know that work done for a closed system is PdV. Okay. So from here, since pressure is nothing but constant over volume to the power of gamma. So put that from initial state to final state, constant over volume to the power of gamma dV. So that is constant initial to the final dV over V raised to the power of gamma. We know the integration of it. Very simple from the mathematics. So that is V to the power of 1 minus gamma over 1 minus gamma from initial to final. So that is C V final 1 minus gamma minus C V initial 1 minus gamma over 1 minus gamma. And we know that constant is nothing but what we can write. In the term of pressure. By pressure by V raised to the power of gamma. So you put back constant as it, since constant is nothing but PV raised to the power of gamma. Put this constant back. Yeah. That will be PV raised to the power of gamma into V 1 minus gamma minus PV raised to the power of gamma initial, final, pressure final and v raised to the power of 1 minus gamma over 1 minus gamma. So this term in a whole will be v final only. Okay. Because gamma gamma cancels. V final minus p initial v initial, okay, upon gamma minus. That is your work done. Very important relation for an adiabatic process. Similarly, we know that PV is nothing but MRT. You can write in that terms also. Work done as MRT final minus the initial that of gamma minus 1. All right, any doubts? Either of them you can use. Okay. Any doubts you have, please ask. I'll give you a minute to go through that, then we'll join. We'll start again. Okay, let's come back. So here it is 1 minus gamma, 1 minus gamma. Okay. I mistakenly wrote gamma minus 1. So what we can do, we can also write it like this. P initial minus P final V final over gamma minus 1. Okay. So final initial sign change only. Similarly here, it can be T initial minus T final. Okay, very important relations. Okay. Now let's come to the next process, that is polytropic process. So exactly similar to adiabatic process, except some heat interaction takes place here. In adiabatic process, no heat interaction is there, but here heat interaction also takes place. And it follows PV raised to the power of n is equal to constant, where n is your polytropic index. Okay. So heat interaction takes place. It follows constant. Okay. Where n is nothing but polytropic index. Okay. So here you can say that heat interaction is not zero. Change in heat interaction is not zero. Okay, unlike adiabatic. So it's the formula for the work done will be again same. P initial V initial minus P final V final over n minus 1, or in terms of T you can write mR T initial minus T final. Same, only from gamma it changed to this n. Okay, this is your formula. So what is the range of n? It's generally from 1 to gamma. Okay, the adiabatic index. It varies from 1 to adiabatic index. But in books, it is generally taken and can have value from minus infinity to infinity as well. Okay, any doubts? Pretty much simple. Okay, no doubts. Now we will represent all of these processes on the PV curve. Pressure volume curve. Okay, very important curve to understand. So suppose oh sorry. This is my pressure versus volume. Okay, so first I'll make a cross like thing. From here we will start. So if my pressure is constant, that is an isobaric process. If it's an isobaric process and expand, okay, is there. Isobaric process is there. So this is your first process where pressure is constant. Okay, isobaric. So expansion is happening from, suppose your original state is 0 and it is going to some state that is A. So here expansion has happened. So process is P is equal to constant, and here your N is equal to 0. N is this N, polytropic. n is 0. Pressure is constant. That is why if you put n 0, v to the power of 0 is 1, p is equal to constant. Next, an isothermal process where n will be 1. So PV is equal to constant. So it's a rectangular hyperbola. So here, expansion. I'm talking all about expansion from O to P. Next is adiabatic process, O to C. That also follows the same. And last one is, you can choose polytropic, T. All are expanding from O to A. Volume is increasing in all of the aspects. So first is pressure is equal to constant. Second is isothermal. Third one is adiabatic. Last one is polytropic. Now question might come, why the slopes of polytropic is higher than, higher than adiabatic, and adiabatic is higher slope than isothermal. The last process is, this process also we should write. Constant volume is this. So constant volume, so this is a V is equal to constant. And here the index n should be infinity, right? Since change in volume is 0, then only it can happen. So here index n is 1, here index n is gamma, and last n is n. Okay. This is for expansion. What will happen in compression? It's just a reverse of it. Okay. Why? Let me first make, then you'll understand why I'm saying all this. So pressure constant, same in compression from O to some state, it will go again O to A dash, and constant volume again A, B, C, D. Suppose I say this is E, so it is E dash constant volume. And now if you see, the isothermal will have a higher slope during compression than adiabatic, than polytropic. So it should be like this. It's a compression, so volume is decreasing here if you go from here to here. Okay, so it is B dash, then I have adiabatic, C dash, and finally D dash polytropic. Okay, all of them are compression process. Okay, so I'll write here, this is expansion. And this is all about compression. This color won't work. Let's take some another kind of color. Okay, this will work. No. All right, let's take this only then. This is compression, expansion, compression. Now the question arises, why I have chosen the slopes during expansion to be higher in polytropic, whereas in compression it is lowest slope. Okay, this is nothing but your slope. Okay, so it's a smaller slope, a higher slope, much higher slope. Okay, for same change in volume, the vertical heights are higher. Okay. Why? Let's see. What is slope? We know that PV raised to the power of n is constant. Okay. So if I do the differentiation of it, we get the slope dp v raised to the power of n plus d n v to the power of n minus 1 is equal into dv is equal to 0. Constant differentiation is 0. So what is dp over dv from here? It's nothing but k times minus p by v. Okay, k times minus p by, oh sorry, n should write k, right? And n is 1, 0, infinity, whatever, according to the process. And since slope is negative, that's why in mathematics also it came out to be a negative value. If you see, all the slopes are negative. The slope is a negative slope. This is also a negative slope. All the angles are negative here. So that's why it came. So what is happening is that the slope is n times of minus p by v. dp by dv is your slope, and it is n times of something. So when expansion is happening, when your volume is changing, so higher the n, higher the slope. Volume is positive. If this is positive, this is positive. So higher the n, higher the slope, and in a negative slope. So in expansion process, if you see, isothermal is n is 1, adiabatic n is gamma, and polytropic n is n. Oh, sorry, I miswrote. N should vary from, so this should be mistaken. This should be polytropic. Here n should be n, and here it is adiabatic. So here n is gamma, because we know that n varies from 1 to gamma. So gamma is a higher value. Sorry. Okay. So we know that n is higher for adiabatic, and all of this is a positive value, negative value, but with a higher slope depending on this value of n. Okay. So higher the n, higher the slope during the expansion process. Whereas if during the compression process, this value be decreased. Okay. So higher the n during the compression, volume is decreasing. Higher the n, lower the slope will be there, because volume is decreasing. Okay. So that's why we have written for adiabatic process, the slope is less during the compression compared to the others. Oh. Yes. Right. I'll run this. Okay. So I'll write all these points. I hope everything is clear now. Okay, note. Slope of adiabatic process is gamma times slope of isothermal process on pressure volume curve. Okay. So when your n is 1, then your dp by dv is minus p by v for isothermal. When n is n, so your dp by dv for polytropic is n times minus p by v. Okay. Or also you can write n times dp by dv. Okay. Since pv is equal to constant here, p raised to the power of n is constant here, and when n is, you say gamma, then your slope will be dp. For adiabatic process, it will be gamma times minus p by v for, okay, dp by, or you can write it as gamma times minus dp by dv, sorry, plus dp by dv. So we see that dp by dv of the adiabatic process is higher than the polytropic than isothermal. Okay, we say that, or to not to get into confusion, you can remove this part and just speed in here. So we can say that dp by dv for pv raised to the power of gamma is equal to constant is greater than dp by dv, the slope, for pv raised to n is greater than dp by dv of temperature is equal to constant, or pv is equal to constant, you should say. First is adiabatic, then isothermal, then polytropic, then isothermal. Okay, and by this statement, I mean that gamma times the dp by dv of adiabatic is gamma times dp by dv of isothermal process. Okay. One thing to note here that value of the index is increasing in clockwise direction. If you see here, n is 0, then 1, then n, then gamma, then infinite. Okay. So polytropic index value is increasing in clockwise direction. So if I go here, so I'll write here, separate note. Value of index, whether it's is increasing in clockwise direction. Okay. So if I have a plot like this, of a PV plot, this, there, if you see, this is your clockwise direction. So n gets increased. Okay. So here k is, so n is 0, n is 1, n is n, n is gamma. Okay. Similarly, this happens from this area also. Again. All right. So we are complete with the work done for closed system, expression of work done for closed system work. Now let's come to the open system work. Expression of work. Let's like the expression of open system work for different processes. So it's again same all the process we will go ahead. First process was volume was constant, isochoric. So if you have a pressure volume plot, and it goes like this. Volume is constant here. So let's take pressure is constant first, because that's for the sequence. So if pressure is constant, okay. So from 1 to 2, if you are going, pressure is constant. You'll project this time on the pressure axis because it's an open system work. So if you see, there is work done is minus of VdP. So no change in the pressure. V into 0. So that will be 0, right? Now, for volume is equal to constant process, isochoric, previous one was isobaric. So again, if I have pressure versus volume plot, if a process goes like constant volume, so from 1 to 2, you have to project it over pressure axis. So that will be work done as negative of VDP, negative of from initial to final. Sorry, I should write like this. Initial to final. So negative of V into P final minus P initial, or you can write taking the negative sign inside P initial minus P final. That is a work done at constant pressure or constant volume process. Next one is constant temperature. Third, temperature is constant, isothermal process. Work. So as I said, it's a rectangular hyperbola. The pressure volume. So from here to here, you are going from 1 to 2. Project this on the pressure axis. So work done is ADP from initial to final. Okay. So what is the equation of rectangular hyperbola is PV is equal to constant. Oh, sorry, XY is equal to constant. That's a mathematical equation of a rectangular hyperbola, if you see. Okay. So the work should come out to be same. Okay? If it's a rectangular hyperbola, then work will come out to be same. Okay. Let's see. So rectangular hyperbola. So both open system and closed system work should come out to be same because area is same for rectangular hyperbola, either it projected over the pressure axis or the volume axis. Let's see, does it come or not? Let's prove. So since we know that, someone has tried to join. So since we know that isothermal processes, PV is equal to constant. Okay, so PV is equal to constant, and we also know that our rectangular hyperbola equation is XY is equal to constant from right rectangular hyperbola equation from mathematics. So from here, volume is constant by pressure. I put this work done is negative of V dP. So volume can be written as C over P and dP. Okay. C over V dP. Now integrate from initial state to final state. Take out the C outside. dP over P. Again, it is ln of P final by P initial. Okay. Or what you can do, take this negative in the log, you will get C times ln of P initial by P final. Okay. And since PV is equal to constant, you can write inversely proportional V final by V initial. So therefore, work done is C times ln of P initial by P final, or C times ln of V initial or V final by V initial. And if you will observe, this is the same work that we had for the open system process or closed system process. C times ln V final by V initial, C times ln P initial by P final. And this is also the same which we got for open system works. C times ln P initial by P final, V final by V initial. Okay. Got the same thing. So for isothermal process, both for open and closed system works remains constant always. Okay. Let me write here. Since rectangular hyperbola, that's why the graph of the isothermal process is rectangular hyperbolic in nature. Rectangular hyperbola. And its formula is close, and area is basically area is same for both rectangular hyperbola. Area is same. From graphical as well as mathematical point of view, we have proved that work come out to be same. erase same under PV curve. Okay. And for isothermal process, both for open and closed system, work remains same. Okay. All right. We have done this. Now a note comes here that very important note to point. In case of isothermal expansion process, as volume is increasing, V final will be higher than V initial. So by using the expression of open system work, we get a positive sign. Let me write. In case isothermal expansion as volume increases, okay, by using expression of open system work, for isothermal process, we get positive sign. Okay, that is V final by V initial is greater than 1 because V final is higher. So work done, what was the work done? C times ln V final by V initial, which is again positive because it's greater than 1. Log of greater than 1 is a positive value. Okay. Also for isothermal process, open system and work, open system work and closed system work process remain same. Right? We'll prove again this mathematically also. So from rectangular hyperbola, from graph of it, from the expression of works, and one another way we can prove is that. And yeah, for one more point here, for isothermal compression, okay, if isothermal compression is here, work done will come out to be negative. Okay, work done, since ln during isothermal compression, since V final by V initial is less than 1. Okay, final volume is less than 1. So therefore, work done will be C time ln V final by V initial, as we know, and this is a negative less than 1. So that will give you a negative value. Okay, so this term is less than 1. This ln of less than 1 is negative value. So from above 2 points, if you see for expression compression, negative sign is required in open system work. If negative sign was not there in open system work, then the expression won't be valid. Okay, this would be V final by V initial by V final. The answer would come out to be like this in the expression. When you will solve, this would come out to be V initial by V final. Okay, and log of a negative value will not this, sorry, a negative value will come out inside it. A negative value would come out inside it, which won't be a favorable because log of any negative value is not defined. Log of any negative value is not defined. So mathematically also, if you see that from the above 2 points, negative sign, that is minus of VDP, is required. Okay, that's also we have to prove. From above 2 points, Negative sign is required for open system work. That is negative of VDP. This negative I'm talking about. Okay. Another process that point is that for isothermal process, open system work and closed system work remains same. We'll prove it. Since isothermal process follow PV is equal to constant, differentiate it, you will get VDP plus PdV is equal to 0. Okay. So PdV is negative of, sorry, VDP if you transpose it over the right hand side. Now integrate both the sides. So first we differentiated, then integrated. Differentiate. Now integrate. Okay, and this is your work of closed, and this is your work of open, and both are equal. Work closed is equal to work open. Okay, clear? Any doubts? We'll come to adiabatic process. Give me a minute. Okay, let's start. So I hope no doubt still here, right? You have gone through. All right, let's come back to the adiabatic process, the fourth process. Okay, so we know that PV raised to the power of gamma is constant for adiabatic process. So from here, you can say that your volume will be C to the power of pressure, C by pressure to the power of 1 by gamma. So you can write work done as, so please, negative of VdP, put this V here, negative of C by P to the power of 1 by gamma dP. So C to the power of 1 by gamma is taken out, and dP to the power of P to the power of gamma is left here. Now you integrate it, so it will be minus C to the power of 1 by gamma. If you integrate from initial to final state, so it will be P to the power of 1 minus 1 by gamma, 1 by gamma from initial to final state. So this can be written as minus C to the power of 1 by gamma, gamma minus 1 by gamma, this term, okay, the denominator, and this will be P final 1 minus 1 by gamma minus P initial 1 minus 1 by gamma, okay. P final is P initial. Take the negative sign inside with the C, so you're left with gamma upon gamma minus 1, C to the power of 1 by gamma, P initial 1 minus 1 by gamma, plus minus C to the power of 1 by gamma, okay, P final 1 minus 1 by gamma. All right, so that is in whole your, have I missed something? Okay. Now what you can write C again, C can be written as C to the power of 1 by gamma can be written as PV raised to the power of PV, C can be written as like this, as we know that P V raised to the power of gamma power 1 by gamma. So this C is PV raised to the power of gamma from the adiabatic law. P initial 1 minus 1 by gamma minus PV raised to the power of gamma 1 by gamma final P final 1 minus 1 by gamma. Okay, you multiply both of them. So final result will be of your work done gamma over gamma minus 1. P initial minus P final, P final. And if you observe, it is more or less same like closed system work. Only term difference is this gamma is more. Okay. So work done for open system is gamma times work done for closed system in adiabatic process. Only in adiabatic process. Similar is the case for polytropic process. You know that polytropic process is PV raised to the power of n is equal to constant. So I'll write directly, it will be n times n minus 1 P initial V initial to the power P initial V initial minus P final P final. It's only n times work of flow system. N times work of flow system. Okay. So work done of open system in polytropic process is n time work done of closed system. Okay. All right. Pretty simple, right? We have derived. Okay. So here we finish the topic of work. Now let's come to heat. So a lot of you were earlier having that in the previous tutorial, that what is heat. Yeah. Murugesh, any doubts? I can't hear you. You can type if your mic is not working. All right, let's come to the topic of heat. What is heat? So it's again the form of energy interaction only, but here a temperature difference comes into the room. Okay. So all the energy interactions other than temperature difference are work, but if a temperature difference is coming, then it is called as heat. That's the simple difference between heat and work. Whenever there is a temperature difference, then that kind of energy interaction is called as heat. When there is no temperature difference, that kind of energy interaction is called as work. Pretty simple. Let me write. It is a form of, right here. Energy interaction observed due to temperature difference. That's heat. Okay. So the point to note here is that all the energy interaction other than where temperature difference change is happening, delta T, are work. So heat can be written as, because it's a inexact differential as we did in the last tutorial. So it's written like this, dq, it's a path function as well. So dq crossed is equal to mc delta T is your heat. Okay, is your heat. Very important. Where m is mass, delta T is the temperature, and C is the specific heat of that gas. Okay. So again, there's a sign convention here. So Q given by the system is negative and Q given to the system is positive. Okay. The convention says like Q by system is taken to be negative. Q on system is considered as positive, whereas work done by the system is positive and on the system is negative. Just opposite of the work. All right. Now, what's a specific heat? As I said, C is a specific heat. Let's see. It's a C. Oh. So specific heat C can be written as dq by m into delta T. Okay. So it is nothing but the amount of heat required to raise the temperature of unit mass by unit temperature difference. Amount of heat required to raise the temperature of unit mass by unit temperature difference. Okay. Pretty simple. So it is the amount of heat required to raise the temperature of unit mass by unit temperature difference. And this is a intensive property independent of mass because it's specific enthalpy, specific heat, specific energy, specific anything is independent of mass, and it is because it's divided by mass, right? So independent of mass, it's a intensive property. Okay, we did what is intensive extensive, and the unit of it is, its unit is kilojoule per kg Kelvin or joule per gram Kelvin, whatever you want to write, kilojoule per kg Kelvin. Okay, so some points to note, very important points to note. In case if you have a solid or a liquid of a specific heat, it doesn't depend on the process, whereas in case of gases, it depends on the process. Okay. In case of solids and liquids, value of specific heat doesn't depend on what kind of process you're dealing with, either it's isochoric, isobaric, whatever, constant pressure, constant volume. Okay. But in case of gases, it depends on the specific, it depends on the process, that it's a pressure, constant pressure process, constant volume process. Why? Because if you see the solids and liquids, there are intermolecular forces between solids and liquid particles, if you see, are quite strong. So in a solid particle, the intermolecular forces are very strong, also in the liquid particle. But in the gas, these forces are not that strong. Okay. So when you increase the temperature, then what happens? The energy increases in the system of gas. Okay. And because of that, what happens? The randomness happens in the gases, which increases because of the increase in temperature. And because of which heat generation happens more. Okay. Q becomes more. But in solids and liquids, even if you increase the temperature, it's not that easy because intermolecular force bonding is quite strong. So variation of temperature is quite negligible from which kind of process it's going. Either it's going from constant pressure, constant volume. So that's why there is no specific heat at constant pressure or volume. Whereas for the gases, it is specific heat of constant pressure and volume are there. Okay. All right, let me write this. Very important point. In case of solids and liquids, value of a specific heat doesn't depends on process. Whereas in case of gases, it depends on process. That's why you say that for water, suppose specific heat of water is 4.187 for a liquid, okay, kilojoule per kg Kelvin. Whereas for air, two kinds of specific heats are defined. One is at constant pressure, that is 1.005, which we wrote in last tutorial also, and it is 0.718, and at constant volume. Okay, two specific heats are defined, and the units are kilojoule per kg Kelvin. Okay, why? Let me write the reasons also. Because in solids, and liquids, stronger intermolecular forces are there. Whereas in gases, less intermolecular forces. Okay, because of which, therefore, with increase in temperature, that if you increase the temperature, what happens? Energy increases. That is, you know that half mv square is equal to 3 by 2 kT. Kinetic energy is equal to 3 by 2 kT. Sorry. So with increase of temperature, your energy also increases. Okay. All right. So in gases, what happens? Therefore, in gases, randomness increases and heat Q also increases. Okay. But in solids and liquids, very strong intermolecular forces. Therefore, variation of temperature here is negligible. That's why. So no Cp or Cv here. All right. Okay. Pretty simple. No doubts. Okay. So what kind of general relation is like this? A plus Bt plus Ct square plus and so on. And in solids, if you go ahead like this. At 5 very high temperature, some intermolecular breaking happens between solids. And some melting happens, start to happen, phase change starts to happen. Okay. So like this suppose you are falling around 500 degrees Celsius. Then this follows around, if you go for second order temperature, 1500 degrees Celsius of temperature is when achieved, and so on. Okay. Also, one another assumption here is that value of Cp and Cv in gases are assumed to be constant for a particular gas. Okay. It's assumed to be constant, but in actual it is not. But we assume. So that's an assumption. Assumption, very important assumption. Value of Cp and CV are assumed to be constant for a particular gas. Okay, theoretically we say that. In actual, it is not, because Cp and Cv changes with temperatures. Okay, as you see the above relation, some temperature in gases it will be very high, but in solids it doesn't. This remains constant. Okay, so because when you increase the temperature, so Cp and Cv also increases. Okay, theoretically, let me write this. Theoretically, but in actual, Cp and Cv also changing. It changes temperature. Okay, so what if you increase? This implies if you increase the temperature, then your Cp will also increase and Cv will also increase because of this relation. With higher temperature, Cp and Cv will increase. Okay, but gamma will decrease. Let's see. Gamma will decrease. Let me write here. That is the adiabatic index. Although they both are increasing, but gamma decreases. Okay, let's see how. So how is that? If you increase the temperature in the cycle, the Cp and Cv increases, but gamma decreases in practical way. Okay, so let me write here. Suppose you have a gas. Let me make some short table. You have a Cp, you have a Cv. Okay, you have a gamma. So we'll compare using two values. So suppose Cp is 3, Cv is 2. Okay, let us suppose. So here Cp by Cv is 3 by 2, that is 1.5. Okay, if you increase the temperature on increasing the temperature for some same gas. So as per the statement, Cp and Cv both should increase. Let us suppose Cp increased by 4 and Cv increased by 3. What is 4 by 3? 1.33. You observe that gamma decreased on increase of the temperature. Gamma got decreased. Okay. All right. So that's why if you go with some Brayton cycle or Otto cycle in IC engines when you will study, the efficiency is dependent over the gamma. So there are some relation of efficiency of an Otto cycle. I'll tell you. Is that 1 minus 1 by R some times gamma minus 1. So here gamma is the same adiabatic index. So if gamma decreases, so this term whole decreases, so this whole term increases, and because of which efficiency decreases. That's the issue. So you need to have a higher gamma. Okay. And there are different processes if you see compression stroke, expansion strokes. Okay. So when you observe that, in that scenario, theoretical, because these are theoretical cycles, you will say that Cp and Cv are set to be constant. Okay. But definitely there are temperature changes of the gas. Okay. In when you have an IC engine running. So Otto cycle is a theoretical cycle of an IC engine, very basic cycle. So temperature changes as per the process. So Cp and Cv should also change, but we are not taking that changes, we have made the assumptions in our theory that Cp and Cv will be constant. Okay, anyways, this was to give some extra guidance on things. Oh, all right. Okay, now next point of the note is that value of isothermal specific heat in isothermal process is infinite, whereas in adiabatic it is 0. So value of specific heat for isothermal process is infinite. Why? Because C is nothing but dq by m into delta T. For isothermal process, this is 0. So that's why C becomes infinite. Okay. Whereas value of C in adiabatic is 0, since dq by m into delta T, and this term is 0 for adiabatic process, so that's why it is 0. Okay, clear. Now question comes, I have written here, if you observe that Cp is greater than Cv, then I increased also and Cp is greater than Cv. Why is it so? That can also be a question you guys can ask. Let's do that. Why it happens is that why value of Cp is greater than Cv. So if you see, Cp is a constant pressure specific heat and Cv is a constant volume specific heat. So in case of constant volume process, complete heat is utilizes increasing the internal energy of the system, because the volume will remain same of the system. You can't even expand or contract. Volume is same, the constant volume. So whereas in case of constant pressure process, some part of heat is utilized in increasing the internal energy, as well as some part is utilized in doing the work, because in constant pressure process you can change the volumes. Okay, so we are sitting in ambient pressure. Okay, suppose I have some bottle. I have a bottle. This is at ambient pressure bottle. So if I compress, the pressure is ambient. So if I give some heat, this plastic will melt out. Okay, what happened? Randomness change as well as the volume will decreased. Why? It's at constant pressure. Your volume can change for a constant pressure process. But in constant volume process, you are specifically saying that the process is having a constant volume. You cannot change the volume. Okay, whatever the pressure you changes. Okay. So let me write. Answer to that is, in case of constant volume process, complete heat is utilized in increasing internal energy, and we will cover the concepts of internal energy and so on in the next tutorial when we'll start with first law of thermodynamics. Increasing internal energy of gaseous molecules, whereas in case of constant pressure process, some part of heat is utilized in increasing internal energy and rest in doing some work. So one relation will come that is dq is equal to du, that is internal energy, plus the closed system work pdv. Okay, so we'll discuss this relation in the next tutorial. So constant volume process, this is 0. So whole of the internal heat is equal to internal energy, whereas in constant pressure process, volume is not 0. So you can say that some part of heat is converted into internal energy as well as the work done. Okay, I'll remove this. We'll do this next class. So Q is basically directly proportional to T. Q is MC delta T. Okay, so suppose you have two kind of systems here. There's a piston cylinder arrangement. You are heating with the gas. Okay, and you have another kind of system. So this is initial state. This is final state. And again, you are heating this. So it's a constant volume. All of the volume is constant here. Okay, whereas here pressure is constant. So some volume has displaced of the system. Okay, all right. And since Q is directly proportional to T, so expansion will happen for constant pressure process. All right. Now coming to the types of heat. Okay, I'll write that equation also. No issues. Since V is equal to constant, this is internal energy, this is work, this is heat, and dq is equal to du plus pdv for constant pressure. All right. Okay. Now let's come to the topic of types of heat. Few minutes left, then we'll end the chapter of this tutorial. So there are two types of heat. One is sensible heat, one is latent heat. So first, sensible heat. So for form of heat interaction by virtue of temperature difference is the sensible heat form of heat interaction. By virtue of temperature difference. Is your sensible heat, that is MC delta T, is your sensible heat. So far we were talking about MC delta T, that was sensible. Whereas there is another kind of heat, that is latent heat. Which is nothing but required to cause phase change. Whenever there is a phase change, heat required to cause phase change. So from solid to liquid, liquid to gas. So all the process like sublimation, vaporization, or fusion process, all of them are phase are changing. Okay, from liquid to solid, solid to gas, whatever. So suppose you have an example. Let us take minus 10 degrees Celsius of ice is with you. Then what you did to 0 degrees Celsius of ice. Phase is same. So what will happen? It's a sensible heat, right? It's a sensible heat. Then it is changed to 0 degrees Celsius of H2O, that is water. Then it is changed to 100 degrees Celsius of H2 as well. So again, so this was so far sensible heat SH. Here phase has been changed. So this will be latent heat. Again, here phase is remaining same. So this is sensible heat. Now you change it to 100 degrees Celsius of So here, phase has changed at same temperature. So that is latent heat. Okay, very simple. You have ice at minus 10 degrees Celsius. You get some temperature, it came to 0 degrees Celsius, but phase is same, ice. It's a sensible heat. Then at 0 degrees Celsius only, you converted ice into water. So that's a no temperature change has happened, 0 to 0, latent heat. 0 to 100, you took the water. The temperature difference is there, so it is sensible heat. And from 100 degree to 100 degree vapor, liquid to vapor, change happens, that's a latent heat. All right, so we'll end the tutorial here. I hope there are no doubts. You can watch the recordings of week 1 and week 2 on my YouTube channel. That is YouTube. All the recordings are published. That is Nptel with Varnit. This is the name of my channel. Okay. So my name is Varnit Kapoor. This is my YouTube channel, as well as you will get the sheet of the link as you have enrolled in the course at Nptel. You get the sheet where the PDF of this notes is also there, as well as the YouTube link is also there. For others who are watching this video, apart from the Nptel course, I have added the link of the PDF notes in the group description of the video. Okay, you can click there and get the PDF of the notes. All right, so I hope that we can end the session for today. And I'll see you every Tuesday, the next Tuesday, 6 to 8 p.m. Okay, as per Indian Standard Time. All right, so thank you, everyone.